Section 1.1 is called Mathematics and Problem Solving. And this is where you're going to be very grateful that you have this sheet of paper all printed out so you don't have to write it all, right? There's just a few things to fill in different places kind of deal, and that's it. So what we're going to do is this problem-solving strategy is called Polya's four-step problem-solving process. And the first step in solving problems is to understand what the problem is. So actually, read through it, ask yourself some questions like these. Can the problem be stated differently? What is supposed to be found? What do I need? What are the things that I don't know? What information can I find from this problem? And what information, if any, is missing or not needed? One of the maybe flaws, you could say anyway, in textbook kind of questions is very seldom do they put extra information that's not needed in there. But in real life, that happens all the time, right? There's all sorts of information that you have when you're trying to solve a problem that may or may not really apply to what's going on at all. So it's not a bad strategy to think about when you're looking at things too, that problem does really occur. The second step is to, after you've figured out what they're asking you to do, is to devise a plan. How are we going to do this? And the following is a non-exhaustive list of strategies. So non-exhaustive means I haven't listed all of them. This is just a good selection, but there are other things you could do too. So patterns are fantastic, depending on what you're working with. Looking for patterns could be very helpful. Examining a related problem. I know you guys have done this before. It's the same thing that happens when you say, oh, look, problem number 13 is a lot like problem number 14, and on problem number 13, this is what I did, right? And you do that all the time in mathematics. Examine a simpler or a special case. So this would be the idea that if I have 50 people coming over for dinner, and how many chicken legs do I need? Well, it might be helpful for me to think about my family of 5 or 6 or 8 or however many I normally cook for, and then do something with that smaller scenario to then figure out how much I need for something bigger. So looking at something a smaller case. Making a table or a list. Absolutely love lists and tables. I have a to-do list on my desk or in my bag at all times. I'm a list person. This helps me a lot. And so keeping myself organized in a list or in a table when I'm trying to figure something out is often helpful for me. So it is another strategy. A few more. Identify a sub-goal. So a sub-goal would mean like I need to get to this point. Once I get to this point, then I know what to do next. Sort of like breaking the problem down into pieces. Diagrams. Do any of you diagram things when you draw them? I mean, when you're doing mathematics with them? Sometimes it's really helpful. I'm going to show you one that maybe you wouldn't have thought to do that way today, to kind of get your mind to thinking how diagrams might be helpful with you in that. Guess and check. Did you know that's a legitimate mathematical problem-solving strategy? It really, really is. Guess and check can be very useful. So we're going to take a look at one of those. Working backwards. I know you've worked backwards before. It looks like this in practice when you've probably done it. You've said, I don't know how to do this problem. And you say, oh yeah, the answer's in the back of the book. And you look at the answer and say, how did they get 22? And you look back at the problem and you think, oh, I can see how they got 22 now because I worked backwards. I started with the answer and I figured out where to get back to the question. And so that's one place I know where you've used working backwards. We'll see another one of those. Write an equation is sort of listed last, not because it's not useful, but because we're going to try to avoid that as much as possible. Most of the things we can do can be done without the equations at the level that the content that we're looking at is geared towards. And so the equations aren't necessarily necessary. They're useful. Sometimes they're a lot easier than the other strategies we employ, but they're not necessary. And so we can do some things, and you'll see some things here where you're like, oh, I would have just done that with equations. And the answer is, yeah, you could do that with an equation. But if you're in 3rd grade and your teacher hasn't talked about equations yet, you probably couldn't do it with an equation. So we want to have another strategy for thinking about that. All right, so once we have figured out what plan we're going to attempt to do, we're going to carry out the plan. So we're going to implement the strategies from the step 2 and then perform any needed actions or computations. We're going to attend to precision in language and mathematics used. So if it says some math kind of word that we know means multiply, we're going to make sure we're multiplying instead of adding or something like that. We're going to check the steps as we go along, either formally or intuitively. So formally means double checking to make sure that when I multiply 3 times 7, it's the same thing as I expected to get. Intuitively means, does it make sense? Is it a reasonable thing to be getting at this point? So in other words, when I multiply 7 by 4, am I getting something bigger than 7? I mean, that's sort of an intuitive sort of check step kind of thing. And then keeping an accurate record of all work. This one for some students just comes very naturally. You're going to keep working from the top down on a page. Other students don't work from the top down on the page. They work all over the page. And then it can be very difficult to try to figure out what's from where, or to look back and figure out where you made a mistake. And so in good strategy is to keep track of the pieces so that you can find them again if you do make a mistake. And then the last thing is to check your work. And there are 2 steps to checking your work. One, deciding if the answer is reasonable. When I taught in Kansas, we always had a question on one of our college algebra tests where the answer at the end was a number of termites. I don't know why it was termites, but it was termites. And we would always sort of chuckle at the students who would write something down, something like 42.73 termites. It's not reasonable, right? I mean, you can't have a 0.73 of a termite. I mean, you have to check and make sure that the answer makes some sort of sense. I mean, is it reasonable? And then accuracy means, is it actually correct? You know, did I make a mathematical error to get something to go on? So those are 2 kind of different, but they're related ideas about checking our work. All right, so what we're going to do is we're going to take a look at several of these strategies. And as we're going through, some of the time we're going to use more than one strategy. We have more than one option. But I want us to focus on one at a time so that you can kind of see how some of them work and maybe a way that you wouldn't have thought before. All right, so this is a famous problem. This one is about a gentleman named Gauss. Gauss is a mathematician. So he grew up, like he's in textbooks and stuff, his name's there and such. But when he was in early grade school, his teacher gave an assignment to the class, intending it to take them a good deal of time. You'll never do that as a teacher, I'm just sure of it. Right? Never, of course not. She asked the class to find the sum of the numbers from 1 to 100, and Gauss answered almost immediately. That's interesting, right? Because most of the kids would do this, right? They'd say 1 plus 2, and then they take that result, and they do plus 3, and they take that result, and they do plus 4, and so forth. And that should take a good deal of time, shouldn't it, to get all the way to 100? But somehow he was able to answer almost immediately. So the question would be maybe how in the world would he have done that? Well, the way he did that was with patterns. So patterns are a great way of summing a bunch of numbers together that have a distinct relationship between each other. So I'm going to show you this one, and then we're going to generalize this in a moment to a different scenario. So the first thing we're just going to write down is the numbers 1 to 100. I mean, we're not going to write them all down. We're going to put a little ... between them. But we're going to write down basically what the kids would have been doing. And on purpose, I'm writing down the first 3 and the last 3. And this is what we're looking for, right? And the first thing I'm going to do is, just for the sake of what we're doing, I'm going to give it a name so that we can work with it a little bit easier. I'm just going to call this name S for sum. So I want to know, what in the world is S? What is this value if I really add all these things together? Okay? So the next thing I'm going to do is I'm going to write the same thing down underneath it backwards. Okay? So I'm going to write 100, 99, 98, and then 3, 2, 1. So both of those are S, right? I mean, they're the same thing. They're exactly the same quantity. And here's where the fun starts. We're going to add these 2 equations, I mean that's what they are, together. So what happens when I add S plus S on the left? You get 2S, right? That's the extent of the algebra involved in this right there. There's really not much beyond that. It's just recognizing S and S is 2S. What happens when I add, and I've done this on purpose, we're adding columns of numbers together. What happens, I'm not marking them out, I'm indicating my columns. What happens when I add 1 plus 100? I get 101. What happens when I add 2 plus 99? You get 101. What happens when you add 3 plus 98? You get 101. Do you notice the pattern? Yeah. So all of these things are equal to 101 when they're paired up this way, right? And why in the world is it 2S? Well, I mean, we saw the algebra of what was going on there, right? I mean, we added S plus S, it became 2S. But it's also 2s because I've added it to itself. I've added every number to another number in the sequence, right? And it's really a series. Every number to another number in the series. So I've sort of, in a sense, doubled what I had before, right? There's 2 101s in there, and there's 2 99s in there, and there's 2 76s in there. So I've doubled all the value I had before. All right, so what in the world trick do you know to add a number together to itself, a whole bunch? I have 100s there. How did I get that? Oh, goodness. Those should be 101s. If you just copied down what I wrote, please fix it. I'm sorry. That's better. What trick do you know to add the same number together a whole bunch of times? Yeah, multiplication, right? I mean, if I want to add 101 plus 101 plus 101 a whole bunch of times, which I do, it'd be a lot easier to multiply 101 by what? I don't mean what number, but by what concept? What would I be looking for? Exactly, Amanda. I need to know how many of them there are, right? So if I had a simpler case, think about it. If I had 5 plus 5 plus 5, an easier way to do this is to do 5 times 3 because there are 3 5s, right? The same thing's true for my list of 101s. I just need to know how many 101s there are. So how can I figure that out? Any ideas?
Well, there's 100, isn't it?
Yeah, why?
Because you're doing each number.
We're doing every single number. That's really important. I'm not skipping anything. Like, it's not just odds or something like that. That would make a difference. And because I actually start at 1, right? And I go all the way up to 100. There are 100 numbers in my list that I started with. So there's still 100 numbers in my list that I'm currently working with. It didn't change anything. The numbers changed, but the number of numbers did not change. So I actually have 100, I'll call them terms. Very specifically, you could call them add-ins. Numbers that you add together are called add-ins. But there's 100 terms. So I have 100 of these 101s. So if you have your calculator with you, if you want to do it real quick by hand, what is 100 times 101? 10,100 is correct. And then that's actually double my sum, right? That's twice as much as I really needed. So how do I find out what my original sum was? Divide by 2. Right. So the sum of the numbers from 1 to 100 is actually 5,050. Now, truth be told, Gauss didn't even write any of that down, but he did recognize that there was this pattern, this ability to add the first number and the last number together and sort of work his way in and adding these numbers together to get the same quantity. And then he could use other concepts to make it easier on himself, using multiplication and then division at the end to add the numbers together quickly. Now, this is just one example. We're about to do another one that's very similar. Any questions on this one, though, before I go to the next slide? Okay, so this slide is an example of the strategy, examine a related problem. This is a related problem to what we just did, right? It's not the same, though. I mean, it's not the same numbers. It's not the numbers from 1 to 100. There's not even 100 of them. So when we're looking at these numbers, we're going to have the same kind of process we did before, but none of the numbers are really going to match up the same way. So what did I do as my sort of first step last time? Do you remember? I need to add 2 of them together. Okay? So what I'm legitimately going to do, my first step, is I'm going to write down S equals, and I'm going to write a list of these numbers. You can use the numbers already on your list if you want. And I'm not even going to worry about the fact that there's 3 at the beginning and 2 at the end. I just need mine a little bit larger on my screen. And then what do I put underneath it? Well, I put another S equals, but what do I do with my numbers? Yeah, I flip them backwards. So why in the world am I doing that? Any thoughts?
They're the same, like, numbers. Like, I don't know.
I mean, why do I want them in reverse order? I probably should ask the question a little bit more clearly.
So that you
1 and 100, it's a lot easier like in our head, if that makes sense. But 36 plus 147 is.
Okay, so if I hear you right, I think you're saying that we're wanting to somehow visually see pairs of numbers. Does that sound right, Caitlin? Okay, so like this right here and this right here, if we've written them in, sort of ascending order one time and then descending order the second time, we can see the pairs really clearly, which is really nice. And the reason that these pairs are so nice is because they all add up to the same thing, right? What do they all add up to this time around? What is 36 plus 147? 183. So we've got a bunch of 183s, right? We'll deal with how many specifically in just a second. So right now I've written down the right-hand side of this list, all the 183s added. What goes on the left-hand side? 2s. Because I doubled the values, right? I had original list and I added the list to it, thereby doubling my sum that I originally had. That's really what the 2 is for, is it's saying I've doubled my sum. Okay, now the question is how many 183s do I have? Because that's what I need to know next, right? How are we going to figure that out? Okay, so you want to take 147 minus 36. Does that look right?
Yes.
You are very, very, very close. There's one tiny little piece we have to fix. Amanda?
If you would do that with like the 1 minus 100, you would only end up with 99. So
That's
you're one
true.
off.
That's true. Like if we had done that with this list, which we could count pretty easy, so we wouldn't have to think about it that way. And if we really did the last number minus the first number, we would have been one off. Right? Okay, so any idea of what's wrong? And it is just a very slight thing. It's just one off. What's wrong with the 147 minus 36?
You're counting 136 too. Like,
Yeah, we need to make sure we count the 130, not the 136, but the 36, right? We include the 36 in our count. So instead of subtracting 36, we really should subtract 35. Now, I'm going to explain it in a little different way again, too, but that is what's going on. We really want 147 minus 35. So here's how I think about it. Let's say instead of having a list that went from 36 to 147, we had a list that went from 1, okay, started at the very beginning, all the way to 147. How many numbers would that be? 147. We don't have any problem when things start with 1. That's very clear in our minds. 147 numbers. But we don't have the first 35 numbers, do we? We don't. Our list doesn't have those first 35 numbers. So when we take the big list of 147, it's the first 35 numbers that are removed that we don't have. And that's why we want to leave the 36 in there, is because it actually is in our list of numbers. So we're actually subtracting the number before our list starts because that represents all the numbers prior to the number we started with. It's kind of cool, huh? It's one way to think about it. So what is 147 minus 35? So there's 112. Is that what I'm hearing you guys say? Numbers. Okay, what's my next step? Almost. We haven't done that yet, though. What? Maybe. What? Okay, I need to write down that I'm going to multiply something. Right? Fair enough. Okay, so I'm going to multiply 183 times 112. And I do need the notation to continue correctly. What's going to go on the left-hand side of this? 2s, right? Okay, and then we're going to do what you were suggesting, is we're going to write the division by 2 next. Yeah. So you're going to grab your calculator, 183 times 112 divided by 2. We're going to end up with s equals something. What'd you guys get? I know some of you were just getting your calculator out then, but did anyone have it out and have the calculation done? 10,248. Do I have a second on that? Got some nods. Okay, good. Yeah, that's it. 10,248.
question.
Yes, Tasha.
Why, if you, instead of using the 36, you use the 35,
why wouldn't you do with the 147? Why wouldn't it be like 148? Did I include the 147?
The first number tells you how many numbers you have total in the list. There were 147. If you went from 1 to 147, you'd have 147 numbers. The subtraction is just the removal of the part that you're not using. That's why.
Sorry.
Yeah. No, it's okay. You're fine. Any other questions on this one? Think with me for a moment. Both of these examples listed every single number, didn't it? Like all of the numbers from 1 to 100, all the numbers from 36 to 147. What if it listed every other number? What would you have to do?
Divide how many numbers you have by 2.
Right. You'd have half the numbers, right? So like, let's say you only had even numbers between 1 and 100. Well, how many even numbers are there between 1 and 100? 50, right? What if you had every fifth number? What if you went 5, 10, 15, 20, 25, 30, and so forth? What would you have to do? You have to divide it by 5 because you only have every fifth number, right? So that's a variation of what we can do with this problem as well, is it doesn't have to be a list of every single number. It could skip numbers. Now, it has to do it in a pattern form. We can't randomly skip numbers, but we can do it with skipped numbers as well. All right, let's take a look at a go a little bit different direction. This is a good strategy for examining a simpler case. A soccer league has 10 teams, and each team plays every other team once. How many games will the league manager need to schedule at the start of the season? It's a very practical problem. Leagues of things all the time, you'd need to know this in order to get the games scheduled, in order to get the referees planned, and all that kind of stuff. So, but 10 teams is not real helpful. So we're going to take this scenario and make it much smaller. We're going to do it with 3 teams, just because 3 is easy to work with here, okay? So I'm going to do it with 3 teams. And for what we're going to do, we're going to give those teams the letters, names A, B, C. And what I want us to do is I just want to write out every combination of 2 teams that can play each other. For example, we could have the game that's A, B. What else could we have? Try to think organized so we don't miss one. What else? A, C. B, C. A is a team, so A can't play himself. They would practice against themselves probably, but not to play themselves. Now, technically, if we write every combination, you might be thinking, or it would actually be a permutation, but you might be thinking that you could also do something like this. Listing the other version as the first value, right? I mean, that's really what would happen, right? So do you see C listed there in multiple places and so forth? Yeah. But this is sort of the natural inclination to think that I would just end up having, every team as the first team, like the home team or something like that, and to go with that. The problem, of course, is that this is duplicating games, right? So this is on somebody's roster that they're going to play A, B. And somebody else in their mind, they're saying that we're playing BA, but this is the same game, right? It's the same people that are playing. It's the same game. And if they're only playing each other once, I can't have it listed twice. So this sort of looks like that we have 3 teams times 2 because I have 6 games, right? Before I noticed that some of them looked like they're double counted somehow. There's 3 teams, and they each play 2 games. 3 games, 2 games, right? Okay. But like we said, this has got a double counting. Everything I listed in my second list was already in the first list. It was doubled. It was duplicated. So in very much the same way as we divided by 2 over here to remove the fact that we doubled everything, we're going to also divide by 2 over here to remove the fact that we doubled everything. So the 3 is the 3 teams. The 2 is the number of games per team. And then why in the world was it division by 2 again? Where'd that come from?
Because there's double games.
There's double game. I doubled all my games, right? I double counted something. Counted something twice. So this is my doubles, my double counts. And they get removed. Okay, but that is just 3 teams. And can you imagine, this is why I don't want to do it with 10 teams. I don't want to write letters A through whatever, all 10 letters, and write every combination of A with every other team and B with every other team and C with every team. This would take me a little bit of time. Doable? Yeah. But not especially fun. I mean, I don't want to do that. I'd rather look at the pattern that was just established by what I just did. What I just found out is my number of teams can be multiplied by the number of games the teams play. But when I do that, I end up with double counts that I can remove by dividing by 2. So let's try that with our games. How many teams do we have? What was it? 10. We have 10 teams. How many games will each of the 10 teams play?
1.
Well, they'll play every team.
Okay, so 10.
So they'll play 10? 9. They will play 9 games. Why is it 9 instead of 10? You caught yourself, Caitlin.
So you can't play yourself.
Right, you can't play yourself. So there's 9 other teams. So whatever team Eagles are or whatever, they've got 9 opponents that they have the opportunity to play. So I mean, legitimately, they are going to play 9 games. Every game, every team is going to play 9 games. Every team. Okay, but if we list them all in that way, I double count everything. So what do I need to do with my 10 times 9? Divide it by 2. Because I'm double counting, right? Basically what we're saying is that if I'm on the Eagles team, I play 9 games, and you're on the Hawks team and you play 9 games, and you're on the Ravens team and you play 9 games. If we added up all of our 9s, the problem is that one of my games and one of your games got double counted, right? Because they were on both of our lists. So we have to divide by 2 to remove that double count. What do you get when you take 10 times 9 and divide by 2? 45 is correct. So there are 45 games that will be played under the constraints of this particular setup. And could we apply this in other scenarios? I mean, could we have a bigger set of games? Could we have 20 people playing, 20 teams playing? Sure, easy. And so we took something that was very simple, 3 teams, and we made a generalized solution that we could use for anything now, because we part it down into something smaller to work with. All right, let's take a look at another one. This is a wonderful example of where a diagram can be used, but it's probably not your first thinking because you've had too much math to think of a diagram in this particular scenario. So let's take a look at the scenario. A store sells bicycles and tricycles. There are a total of 15 cycles in the store. And there are 35 wheels on those cycles. How many of each type of cycle are in the store? So this looks a lot like a problem you probably saw in something called Algebra 2 in high school. And do you remember how you approached it there? Probably wrote some kind of an equation. Something like x plus y equals 15, and you did something like 3x and 2x and something about the 35, and you did some sort of a substitution or elimination or graphing. And those are some advanced algebra techniques in order to get that problem done. So I'm going to show you another way to do it that's really manageable at a young age, because this is really fun. Okay? Here's what we're going to do. We know that we have 15 cycles, right? So if your artistic skills are better than mine, you're welcome to make a bicycle look like a real bicycle. This is what my bicycle is going to look like. That's my bicycle. Okay? And I'm going to draw 15 of these bicycles. Okay? So you draw 15 as well, whatever you want your bicycle to look like. Okay, I've got 15 funny-looking bicycles. Do you have 15? Okay, without counting, you can tell me real quick, how many wheels are currently on my cycles? 30. How many wheels am I supposed to have? How many wheels am I missing then? 5. So what would I need to do to my pictures? I need to add 5 wheels. And I have to add them one at a time because the other image in this particular description is tricycles, right? So if you thought my bicycles looked funny, this is my tricycle. I think they look a little bit like cherries. I mean, did I do it? Do I have 35 wheels? Do I have 15 cycles? Yeah. How many bikes do I have? Ten. You guys are saying you just don't want to say it out loud. That's fine. 10 bikes. And how many trikes? 5. Now, come on. Isn't that a clever way to do the problem? It really is. It's quite clever, and you'll be surprised. It will come up on standardized tests for kids that are quite young because they can do this. This is totally a legitimate process. There's nothing in this here that you probably couldn't do in about 2nd or 3rd grade, right? I mean, all I did was draw pictures and I made circles and, I counted and that's it. And I answered the question, which is pretty cool. All right, let's take another one. This one's got a bit of a diagram with it as well. All right, we have, this one says make a diagram. It has a double strategy. I think on your paper it says guess and check, doesn't it?
Yeah.
Yeah, we're going to do both. I probably couldn't decide which one I wanted it to say, so I picked one place on one place on the other. So we're going to do a guess and check strategy with a diagram on this one, and a table for that matter. I mean, we could just throw 3 of them all in one. We're going to combine them. We're going to have all sorts of fun. All right, we have 48 feet of fencing, and we wish to make an enclosure along one side of an existing barn. What lengths would the sides need to be in order to have the greatest area enclosed for our chickens? Do any of you have chickens? Oh, we do. Wonderful. What fun. Okay, we're going to draw a barn first. I've got an existing barn. That's my barn. Yeah, I know. You guys are going to have so much fun with me this semester in my drawing. That's my barn. We're going to make an enclosure along the side of the barn. So if you think just practically, what this means is we're going to make some kind of a fencing next to the barn, but the fencing is not going to go actually beside the side of the barn, right? Nobody fences like that. If you guys have fences in your backyard, you know what I'm saying. The fence does not line your house. You don't go around all the way the house, right? It's away from the house. The point is for it to be enclosing, and the house actually forms part of a wall, if you will, to it already. Same thing for my barn. So what I've got going on over here then is I need an enclosure next to it. Let me use this color. Like this. Not like that. Let's try again. That might be a little bit better. So how many sides does my fence actually have? Actually only has 3. It's a rectangle, but it only has 3 sides because that barn is automatically providing the 4th side for us. What else can you tell me about this particular shape and these particular sides? Two of the sides are the same length, at least 2 of them, right? Yeah, the top one and the bottom one. And so we'll call them W for width at the moment because the way I drew it looks like it's the short side. It may not happen to be, but we can call it W. And then we'll call the long side L for length. And you can use whatever letters you so please, but this works pretty well. You don't even really need letters, but we do need to think about it in terms of the fact that there are 2 sides that are the same. That's important for us, so that's why I labeled it. All right, so what we're going to do next is we're going to guess. So we're going to guess some things, and we're going to check them as we guess them to see what happens. And we're going to do it sort of in a list form so that we can keep track of what we're doing and make sure that if we make a mistake, we have a way to go back and check it and figure out what's wrong. All right, so the first thing I need to be aware of the fact that I have a certain length of fence possible. All I have is 48 feet of fencing. So I can't have a side length, for instance, that's 52 feet long. That doesn't work, right? So whatever I pick, I need to be picking numbers that are smaller than 48. And really, actually, like, much smaller, because I've got 3 sides. I can't just have one side. That would give me nowhere for my poor chickens, okay? So I need a suggestion. What would you like W, or the width, to be? What would you like to try first? 12? Okay, 12. So if I do that, I've got 2 sides that are 12, right? And then if I have 2 sides of 12, what would the other side of the fence have to be? 24. And why do we know that? Yeah, they all have to add up to 48, right? I've got 2 12s, and then I've got a 48 foot. We want to use it all up. I mean, obviously, we're going to get more space inside if we use all the fence instead of leaving some left over. All right, so what am I going to do? What do you think this check business is? What am I checking in this particular problem? The area. I mean, what did we find? Well, it wanted me to find the greatest area. And maybe I should have boxed it in better. The greatest area enclosed, actually. So I've got 3 numbers here, 12, 12, 24. What in the world am I going to use, and how am I going to find area with those numbers? Right, 12 times 24. Because 12 is the width and 24 is the length. So what is 12 times 24? 288. Do you know what units should be on that? Feet squared. You can write it like this, or if you prefer, you can write the SQ feet like this. It's another way to write that. Either of those options are fine. I get the feeling that when this answer was picked, somebody knew that this was supposed to be my answer before we started. Don't get the feeling that it was just actually random. So if you happen to pick the answer correctly, and even if you don't, what would you do next? Because I can't just say I found one, that's the largest one, because I didn't really show that this is the largest one as of yet. What would I have to do next?
Just try different numbers.
Yeah, I need to try different numbers. So somebody give me another set of numbers to try, something different than 12 to start with. Can I do 10, just for fun? Okay, let's do 10. 10, and the other one would have to be 10, and then how much would be left for my last side? 28. I like 10 because the math is easy. So what does my check step look like? 10 times 28, which gives me 280 square feet, right? Whoops, I said it right, wrote it wrong. Let's write it right. Is that more or less than the first one? It's less. So do I know for sure that the first one's the biggest? No, I just know it's bigger than the one I already have, right? What else do I need to check? I mean, like, that's good. Making it 10 didn't work, but now what? Well, I'm inclined to think that if I tried 10 and I tried 12, I better try the number in between, because it could be bigger. That's a possibility. I certainly am going to have to try it at some point. So let's try 11. What would the third side be if I had 11 and 11? 26 is correct. Good job. And then we want to figure out what is 11 times 26. 286. Again, smaller than the first number, right? So I have this sort of feeling then, and notice if I'd done them sort of in descending order, it would be a little bit more obvious. But look at the 12, 12, it's 288. 11, 11 is 286. 10, 10 is 280. What's going to happen if I go to 9 or 8 or 7? It's going to keep getting smaller. So do I need to pick and try and test anything any smaller than the 10 already? No, I don't. I can already see that the pattern that's established by what I already did is it's going to go down. But I do need to check something else. What do I still need to check? The other side of 12, something like 13. And so since I'm sort of leaning towards the idea that maybe 12 sounds like a good answer anyway, we are just going to jump to the 13. So if I had 13 and 13, what would my third side be? 22. And then I'd need 13 times 22, which is what? 286. And just for fun here, I'm going to do one more, not because I absolutely need it, because I want to show you some really nice symmetry that's involved here. What if I did go up one more? Well, I'd have 14, 14, and 20. And what would happen if I did 14 times 20? I get 280. Right? So on either side of the number 12, if I go slightly smaller than 12 by 1, I got 286, and then I got 280, and then now slightly bigger, 286 and 280, right? So what's going to happen if I keep giving bigger numbers? It's going to give it smaller values. Now, you might be looking at this and saying, okay, I was pretty sure that the 12 was right to begin with, so what do I actually have to show that I really know that that's the fact? Like, what's the bare minimum in this table that proves this works, or gives reasonable justification for it working? Well, what really gives reasonable justification is this one, and this one. The numbers on either side of 12 being smaller than 12. The 12 in the middle being the largest. That's the minimum in this table that actually is necessary to sort of justify that the answer should be 12. And in fact it is. I mean, that is correct. Now we do need to be careful about what question is asked. What are we actually giving an answer to? What lengths? What lengths would the sides need to be? So what would the answer be? Okay, I'm going to change it just slightly. I'm going to say 12 feet, and 24 feet. So we want to make sure we include units whenever there are units to include. Now, what if this question had asked the question differently? What if instead of saying what lengths would this have to be, it said what's the maximum area that I could enclose? What would the answer be then? 288 feet squared, right? So you do have to be mindful that the same question, slightly different questions could be answered by the same work, and you need to make sure you're answering the right question. Okay, this next one just takes like tiniest little bit of time, so we're going to do it real quick. Working backward. I told you we'd do an example of working backwards, and this one's a cute one. All right, one winter night, the temperature fell by 15 degrees between midnight and 5 a.m. By 9 a.m., the temperature's numerical value had doubled from what it was at 5 a.m. By noon, it had risen another 10 degrees to 32 degrees. What was the temperature at midnight? All right, so I just have this feeling like I have to write these times down so I can get some sort of a perspective on what times are all involved, because there's a lot of list of numbers. This is a lot of times involved. So what is the first time that's involved in this problem? Midnight. What's the second time? 5 a.m. Now, why they're up at 5 a.m. to check the temperature? I didn't ask, but all right. What's the next time? 9 a.m. And then what? Noon. The next thing I'm going to write down is how the temperatures are changing. Almost everything in this problem describes how the temperature changes, not really the temperature itself, right? Just what's happened to it. So the first one actually talks about what happens between midnight and 5 a.m. So what happens between midnight and 5 a.m.? It drops. So that's like a negative, right? By how much? 15 degrees. What happens between 5 a.m. and 9 a.m.? Yeah, the number is multiplied by 2. Now, be real careful not to confuse, and I was really careful when I worded the problem. We can't say a temperature doubled. That doesn't even make a lot of sense, because you can't say it's twice as hot as 100 degrees as it was at 50 degrees. I mean, that's using a very specific scale, the Fahrenheit scale, to say that. It wouldn't work if you therefore went back and looked at like Celsius or Kelvin or something like that. So we can't really say the temperature doubled, but the numerical number did. Okay, so that's why that's worded kind of funny. What happens between 9 and noon? It increased 10 degrees. And then they give us one final bit of information that allows us to solve the problem. What do they say? It says that at this point, it equaled 32 degrees. So now we can go backwards. If it was 32 degrees at noon, what was it then at 9 a.m.? 22 degrees. Where did the 22 come from? You're right. Somebody. Yeah, you subtracted 10 because what this actually says right here is that to go from 9 to noon, you have to add 10, right? So if you're going to go backwards, you're going to do the opposite, so you subtracted 10. All right, so what happens if you go from 9 a.m. back to 5 a.m.? Divide by 2. So what do we get? 11. Very good. Then we have one more step backwards. We've got to go from 5 a.m. back to midnight. 26 degrees, right? And then this is one of those ones where it's really, I mean, you should be checking to make sure things make sense all the way along. Like in this one over here, I didn't actually say it, but that's essentially what we were doing by double checking all the numbers really close by. But checking to make sure that this makes sense, let's actually just use the numbers and make sure it works. It says that between midnight and 5 a.m., it drops 15 degrees. Does it do that? From 5 a.m. to 9 a.m., the numerical value doubles. Does it do that? And then from 5 a.m. to noon, the numerical value or the temperature increases by 10. Yeah. Okay, so what was the question asked then? And the answer was 26 degrees. Very good. Okay, let me just make mention of this, and we'll pick up on this next time. I'm not going to read through all these details, but you've got one problem in your group work that you're going to do, which we will do group work next time. I'll pause on that in a second. And it talks about the 12 days of Christmas, which is fun, although it's not Christmas yet, but it is kind of fun. And I wanted you to kind of see, this is a real cool thing that I had found several years ago, that the 12 days of Christmas religious symbolism. And in part, I'm reading it on here because it's cool that it's religious symbolism, and also in part because you can reference and go back and say, oh yeah, day 8, that was 8 maids of milking. That was the maids of milking, because you're going to need to reference that on one of your problems. But just real quick, the true love is God. Turtle doves is the Old and New Testament. 3 French hens are faith, hope, and love. 4 calling birds are the 4 Gospels. The 5 golden rings are the Pentateuch, the first 5 books of the Old Testament. 6 geese a-laying is 6 days of creation. 7 swans a-swimming is the 7 gifts of the Holy Spirit. 8 maids of milking is the 8 Beatitudes. 9 ladies dancing is the 9 fruits of the Spirit. 10 lords a-leaping, 10 commandments. 11 pipers piping, 11 faithful apostles. And the 12 drummers drumming is the 12 points of doctrine in the Apostles' Creed. So some cool stuff.